In the last lecture, we talked a lot about right triangle trigonometry. So finding missing sides and missing angles in a right triangle. Now we're going to take the right triangle and we're going to convert the ideas into a circle. Okay, so we're taking trigonometry and we're looking at it from a very different perspective. And what we do is we start off by looking at something called the unit circle. Okay, so first of all, let's talk about what a circle is. Okay, I don't know if you ever really defined a circle or if you can come up with a definition for a circle, but essentially what you have is you have a single point. That would be your center point. Okay, this is your center of your circle. And then the circle is constructed by taking a distance, a fixed distance, which we call the radius, and every point that is that distance from the circle, from the center, would be on your circle. So up at the top here, this point over here is a fixed distance, it's r, okay, from the center. Now this point is the same distance from the center. We could take a point over here, and this would be the same distance from the center. We could take a point over here, and it would be the same distance from the center. So we could keep doing this, and if we connect all of the points that are that distance from the center, so this is not the best circle, but if we take all of those points, we get a circle, okay? So a circle, the way that we would define it, it would be all points that are a fixed distance r from a single point. Okay, that r is your radius. And this single point here is the center of your circle. Okay, now the way that we distinguish between circles, there are two ways that we distinguish between, let's say, this circle, which I apologize looks more like an oval. I promise you on my paper it looks more like a circle than it does here, okay? But we have two ways of distinguishing between, let's say, this circle and another circle, okay? So if I have a circle here, and then I have a circle over here, the question is, how do we distinguish between these two circles? What makes them different from each other? So we know that they're the same distance from the center, right? They're all the points the same distance from the center. That would be the definition of a circle. But what makes this circle 1 and this circle 2? What makes these circles different? Okay, so there are two things that make two circles different from each other. The first thing is obviously the size. Okay, so this circle is smaller than this one. So size is one thing that distinguishes between them. The second thing is the location, right? So we could have two circles, they could be the exact same size, but they're located in different places. Maybe this circle is over here on the page, and maybe we have another circle the exact same size, but it's over here, okay? So we distinguish between circles using size and using location. So how do we measure the size? We measure the radius. And how do we identify the location? By where the center is. Okay, this is how we distinguish one circle from another. So let's consider something called the unit circle. So the unit circle is on the coordinate plane. The coordinate plane just means the x and y axes, okay, as opposed to, let's say, the complex plane where our axes are complex and real, okay? So the unit circle is on the coordinate plane, and its size, or the radius, is equal to 1, and its location on the coordinate plane, or its center, is at the origin. It's at 0, 0. So in other words, if we were to draw this circle, and don't worry, I'm going to show you an accurate version of the circle as well. So here is our XY axis. And the way that we would construct this circle is its center is at 0, 0. So we're starting at 0, 0. And its radius is 1. So what that's doing is it's saying every point is exactly 1 unit from the center. So the easiest way to do this is to construct the 4 points that are on the axes, because we know what those are, okay? So if we go to the left by 1 unit, then we are at the point 1, 0. If we go up 1 unit, then we're at the point 0, 1. If we go to the left 1 unit, we're at the point -1, 0. And if we go down 1 unit, we're at the point, we're probably over here, we're at the point 0, -1. And then we're going to roughly connect these. I think the more accurate point would be here, probably. Sorry about that. I will show you a nice, accurate version of this. Okay, and if we keep going, okay, this would be our unit circle. So what does it look like when it's drawn well? It looks like this, okay? Ignore the yellow boxes for right now. It looks like this, right? Here's a nice, beautiful circle. We have our 4 points. Our distance, our radius is 1, okay? Our radius is 1, and our center is at the origin. So this is our unit circle. And let's see if I could. I'm just going to do it this way. Ignore me. Here we have our unit circle. Okay, our radius is 1, and our radius is 1, and our center is at 0, 0. Okay? Okay, so what do we know about this unit circle? So first of all, it is a graph, okay? So it does have an equation. So let's figure out what this equation is. So an equation of a circle is a relationship between our x and our y, okay? So let's say, for example, that we have a point x comma y. It's anywhere on the circle. Let's make it over here. Okay, that point right there is the point x comma y. And we need to figure out some sort of relationship between our x value and our y value. So in order to figure out this relationship, we can create a right triangle, okay? So let's do that. So to do this, we're going to draw a line that comes from the origin and it hits this point, okay? Let's make this a little bit thicker so it's easy to see. Okay, so we have this, and then we can actually drop a line as well to the x-axis. And we could do this anywhere on the circle. We can always drop a line to the x-axis. Okay, and we'll make that a little bit thicker also. Okay, so we have a right triangle here. And we know something else. We know what this distance here is equal to. Because if this is equal to x, okay, then this distance here is equal to x. So let's put that in there. This distance is equal to x. And if this distance from here to here is equal to x, then this distance, this vertical distance, is equal to y. So over here, this is equal to y. Okay. Now we know something else. We know what the length of this line is. The length of this line is 1. Because it's the unit circle, this is the radius. This has a length of 1. So no matter where we draw our triangle, this is going to be true. We could draw it over here. We could draw it down here as well. Okay, if we drew a triangle down here, the horizontal distance would be x, the vertical distance would be y, and the diagonal would be 1. And we can come up with a relationship between x and y then, okay? And the relationship is the Pythagorean theorem, okay? So the Pythagorean theorem says a squared plus b squared is equal to c squared. So here's the thing though, right? This is similar to what we were doing when we were trying to identify like all of the different 6 trig functions given one trig function. So you were given the sine of 3/7 and we wanted to know what the cosine was, what the tangent was, cotangent, cosecant, and so forth. Instead of labeling this a squared plus b squared equals c squared, or even opposite squared plus adjacent squared over equals hypotenuse squared, we can use this x squared plus y squared is equal to 1 squared. Okay, or we could be even more general and say x squared plus y squared is equal to r squared this is the equation for any circle with center at 0, 0. But if we want specifically the equation for the unit circle, the equation for the unit circle would be x squared plus y squared is equal to 1. Okay, that's the equation for the unit circle. And just to note that let's say that our center were at 2, 3. Well, if our center is at 2, 3, essentially what we did is we're translating the circle 2 units to the right, and we're also translating it 2 units up. So we would put that transformation inside here. Okay, so let's write that down. We're going to write all of this down. And I'm going to put it into the board notes too because I can include this as a separate file, but I also want it sort of inside here. Okay, so here's what we're going to do. I'm going to make a bigger picture of this. It's not going to be perfect, but you have the idea from the other circle that's there. There's some people who just draw circles so well. So here's our this was not that accurate. Okay, but hopefully you have a pretty good idea. This is awful. Let me see if I can fix it. I think this point has to come here. At least I don't have to see your faces as to how awful this circle looks. Okay, so here's our x and our y. So equation of a circle is x squared plus y squared is equal to r squared. That's because if we take any point x comma y and we create a triangle, a right triangle, and we're going to be doing a lot with right triangles inside circles. This horizontal distance is x, this vertical distance is y, and the diagonal is r. So we're using the Pythagorean theorem to create a relationship between x and y. Okay. But if we want the equation of the unit circle, then in that case, we have x squared plus y squared is equal to 1. Okay. Now this has, just as a side note, okay, this has a center of 0, 0. But not every circle has a center of 0, 0, right? Let's say that our center was at C comma D, okay? What that's doing is it's moving it to the right by C and up by D, okay? if we have our center at 2, 3, we're going to the right by 2 and up 3. That's a translation, okay? So when we move our center, we're translating it. So if the center we're at 2, 3, and if you notice I'm not putting this under the unit circle, that's because the unit circle specifically has a center of 0, 0, okay? But if the center of your circle were at 2, 3, then the equation well, when we go to the right by 3, we subtract. Sorry, to the right by 2, we subtract. And it turns out that what we're doing to y, well, y is on this side of the equation now, okay? What are we doing to y? We would typically take the whole equation and we would add 3 to it, right? But now we're on the other side. Now it's not, we don't have f of x equals x, and then we're adding 3 to the x. We're adding 3 to, we're doing something to the other side of the equation, okay? So if we had, just as a side note, I'm putting it down here, just so that you understand what I'm saying. If we have f of x is equal to x squared, this is like y equals x squared. So if we go up 3, it would be y equals x squared plus 3. On the other side of the equation, we could move it to the other side and make it y minus 3 equals x squared. So notice what's happening here. What we're really saying is happening is that, yes, we're adding 3 to the whole function when we go up. But what's happening to this y value over here when we're on the other side of the function? We actually subtract. So when we talk about circles, we do the opposite for both of them. So we do the opposite for the 2, it becomes x minus 2, and the same thing is true for the 3, it becomes y minus 3. And this is equal to r squared. And if the center were at, let's say, c comma d, then the equation would be sorry about that. The equation would be x minus c squared plus y minus d squared is equal to r squared. And again, it has to do with what side of the equation we're on. So we're affecting not what y is equal to like we are here, we're affecting the actual y. Okay, the individual y, so it would be y minus d. So this is just a side note that if your center is not at 0, 0, what you're doing is you're translating your function, okay? And here's the translation. We go a minus c and a minus d. So the equation of the unit circle, that's not applicable though, because the center is at 0, 0. And our radius is 1. Okay, we could even say something a little bit more here. So I'm going to change this r to a 1, or I'll just write it as r equals 1. Okay, so we could take this even a little further with this triangle. We could say, okay, well, in this triangle, r is equal to 1. Let's say that this angle here is theta. Now, if that angle is theta, then we could take this one step further and we could figure out what the sine of theta is and what the cosine of theta is. So the sine of theta, so this is again in the unit circle. This only applies in the unit circle. the sine of theta is our opposite over hypotenuse, okay? And if we label this triangle based upon this theta, okay, so we have our right triangle, and based upon the theta, we're going to label opposite, adjacent, and hypotenuse. So the y is the opposite, the x is the adjacent, and the r is the hypotenuse. So what does that mean? The sine of theta is equal to O over H. Our O is y, and our H is 1. So the sine of theta is y. Now we could do the cosine of theta. Cosine of theta is A over H. And in this triangle, A is equal to our x, H is equal to 1, so our cosine is x. Okay, why is this important? So when we travel, we can actually travel around a unit circle, okay? So we can travel around any circle on an axis, okay? Let's just take one step back before we do that and make sure that everybody is on the same page here in terms of this unit circle, okay? Because I gave you a lot of information and I just want to summarize it so that you see that it's not complex information, okay? Unit circle is a circle with a center at 0, 0 and a radius of 1. What's the equation for that? It's x squared plus y squared equals 1. Okay, how did we get that? It's just the Pythagorean theorem. We take any point x comma y on the unit circle, and we create this right triangle where the horizontal distance is x. If we wanted to get to this point here from the center, from the origin, we go over x and we go up y, okay? So that means that we have x squared plus y squared is equal to 1. That's the Pythagorean theorem. Okay. Then we can also find the sine and the cosine of this angle here. So this angle is theta, and the sine is opposite over hypotenuse. So when we take this right triangle and we label the three sides, opposite, adjacent, and hypotenuse, the opposite side is y, and the hypotenuse side is 1. So the sine of theta is just equal to 1, is just equal to y. Now we can do the same thing for cosine. The adjacent side is x, the hypotenuse is 1, so the cosine of theta is x over 1, or just x. Okay, you'll see why that becomes important in a few minutes. Okay, when we travel around a circle, we travel counterclockwise. Okay, the opposite of a clock. So we travel around the circle like this. Counterclockwise. We start here. Okay, we start at this point right here. That's our starting point. We also have quadrants, okay? And this is true of any graph, anything on the coordinate plane. This here is quadrant 1, because when we travel around the circle, this is the first quadrant that we go through. We start here. This is the first quadrant. We're going counterclockwise, so this is the second quadrant that we travel through. We can just use a Q. Notice we use Roman numerals. And then this would be the third quadrant that we travel through. And finally, we finish up in the fourth quadrant. Okay. Now, when we create an angle, this side of the angle, every angle is made up of two sides. So this side of the angle is called the initial side, and this side is called the terminal side. Now, we're going to get into that a lot more later, okay? Because we're not going to be looking at specific angles. But what we're saying is that any angle, the sine of that angle is y, and the cosine of that angle is x. So this is the same thing as saying, okay, well, whatever our x is equal to, that's the cosine. And whatever our y is equal to, that's the sine of that angle. So what does this mean? Okay, well, we start here. This is, so I'm going to label the coordinates, okay, the 4 coordinates. This is 1, 0. This is 0, 1. This is negative 1, 0. And this is 0, negative 1. Okay. Now we can also label this in terms of degrees. So when we start, how many degrees have we traveled? We've traveled 0 degrees. Now we keep walking around the circle. When we get to here, how many degrees have we traveled? We've traveled 90 degrees up here. Now we're going to keep walking. When we keep walking around here, how many degrees have we traveled? 180 degrees. Now we're going to keep going. How many degrees have we traveled when we get to here? This is another 90 degrees. So it's 270 degrees. And we keep going because we have to go all the way around. And once we go all the way around, we're at 360 degrees. Okay? So what does this mean? The fact that x comma y is the same thing as cosine theta sine theta. Okay? What this means is that 1 comma 0 tells us the sine of 0 degrees and the cosine of 0 degrees. Okay? The sine of 0 degrees is the y value, so it's 0. And the cosine of 0 degrees is the x value, so it's 1. So this here, let's do brown. This here is the y value at 0 degrees. And this here is the x value at 0 degrees. Okay, we could take this further. We can say that, okay, now we also know the sine of 90 and the cosine of 90. The sine of 90 is the y value, so it's 1. And the cosine of 90 is the x value, so it's 0. Okay? Here, we could say the sine of 180 is equal to 0, and the cosine of 180 is equal to 1. So we're looking at the y value at 180, and we're looking, sorry, this is negative 1. Let me rewrite that. So we're looking at the y value, which is the sine, and then the x value is the cosine. Again, we prove that here, down here. Okay, this is only true for the unit circle. Now we also know that the sine of 270 degrees is negative 1, because that's the y value, and the cosine of 270 degrees is 0, again, because that's the x value. Okay, and in fact, if we go back up here, we can also say the sine of 360 degrees is the same as the sine of 0, and the cosine of 360 degrees also the same as the cosine of 1, as the cosine of 0. Okay, so notice what's happening here. Now we're not working within right triangles anymore, right? Because we're figuring it out based on the right triangle. But a right triangle doesn't have 180 degrees in it, okay? No triangle has 180 degrees in it. So now we're talking about bigger and bigger angles. Now we're going to do this more, but let's add this in to our much, much nicer triangle here. Let's add in the degrees, okay? So we know that this is 0 degrees, but it's also 360 degrees over here. I'll put this right here. Okay. And then over here, this is 90 degrees. Over here, this is 180 degrees. And over here, this is 270 degrees. Okay, so each of these has an angle, and let's put in our theta. I think I have it in here. Okay, so this angle right here is theta. Okay, and we're going to be working with this a tremendous amount. So again, we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. We travel around the unit circle in a counterclockwise direction. Okay, always counterclockwise. So when we start over here, this is 0 degrees. As we travel, this is now 90 degrees. We keep traveling. This is now 180. Every quarter circle is 90 degrees. We keep going. This is 270 degrees. And if we go all the way back around, we're at 360 degrees. Okay. Now, the sine of 0 degrees is the same thing as the y value here. So the sine of 0 is 0. The cosine of 0 is the same as the x value. So the cosine of 0 is 1. Okay, again, we showed that using the right triangle, that the sine of the angle is y over 1, which is y. The cosine of the angle is x over 1, which is x. The sine of 90 degrees is 1, and the cosine of 90 degrees is 0. The sine of 180 degrees is 0, and the cosine of 180 degrees is negative 1. Down here, the sine of 270 degrees is negative 1. And the cosine of 270 degrees is 0. And finally, when we come back to 360 degrees, the sine of 360 is 0, and the cosine of 360 is 1. Okay, so this is the unit circle and everything that you need to know about it, and then we're going to be working with this a tremendous amount in the next couple of lectures. Okay, here's the thing though. When we measure our angles right now, we're measuring them in degrees. But angles aren't just measured in degrees. Angles are measured in different ways, just like distance is measured in different ways, and weight is measured in different ways. Volume is measured in different ways. We have lots of different ways of measuring. We have lots of different units of measurement, right? So distance could be meters, it could be feet, it could be inches, it could be yards, miles, kilometers. We have lots of different ways. And typically we have two systems. We have an English standard system, that's your inches, your feet, your yards. If you're talking about distance, if you're talking about weight, it would be pounds and ounces. Or you have your metric system, which is what's used around the rest of the world. And your metric system in distance, it would be kilometers, centimeters, meters. In weight, it would be kilograms, grams, milligrams. So we have these two different systems, okay? When we measure angles, we have different units of measurement where one unit is in the same system and it might be smaller, okay, a smaller unit of the same thing, or it's in a completely different system, okay? So let's talk about how we measure angles. And then we're actually going to come back to this unit circle. So we have two systems. The first system is degrees, and then smaller than degrees is minutes, and smaller than minutes is seconds. So think of this like your feet and then your inches is smaller than feet. So if I were to ask you what's your height, you might say I'm 5'4". Okay. This is the same type of thing. Minutes is a smaller portion of the degree. Okay. So there are 60 minutes in 1 degree. This is not surprising. Okay, so minutes, what we use is we use an apostrophe just like we would for feet. Okay, 60 minutes and 1 degree. Okay, we're not even going to get into seconds. This is just if you want to say, well, I have 12 degrees in 10 minutes. Okay, minutes is not that surprising. Seconds is not that surprising. A circle, we have a clock. A clock has 60 minutes, right? When you go around the clock, so 60 minutes. And then we have, so it's not surprising that we use minutes as a smaller measurement of degree, okay? The second system is radians. Okay, now you can go between two systems. You can go between radians and degrees, okay? So let's talk about how this works, okay? I am going to try to demonstrate. This is a lot easier if I have a board and I could stand there and show you everything and how it works, but I'm going to do everything I can to make it as clear as possible. So radians, if you notice, it kind of looks like the word radius. That's because it actually is related, okay? So let's talk about what a single radian is, and then we'll talk about how to go between from one to the other, okay? So I'm going to go back to a circle. Okay. Okay, so how does this work? So any circle has a radius of r, right? So if we want to come up with a single radian, what we would do is along the circle, you would think of like a string. You would take a string and you would measure out a length of r, okay? So now you have a string of length r. And instead of putting that string so that one end is at the center and the other end is on the circle, okay? What you're going to do is you're going to lay out that string over the arc of the circle. Okay? You're going to lay out the string over the arc of the circle. And that would be equal to a single radian. So let's use green here. This distance here, would be r, okay? And when we connect this angle would be 1 radian. The angle that we create by connecting the end of that radius to the center gives us 1 radian. Okay, so again, this length, okay, is equal to the radius, and then we can connect this point, the center, to this point at the end of that length, and the angle that we create is equal to 1 radian. If we do this again, so let's take a different color. Let's take this nice blue here. And we're going to lay out again our string that has a length of r. And we're going to connect to the center. And now this has a length, has a measure of 1 radian. So radian is an angle measure. Okay, so now from here to here is 2 radians. Okay, let's do this another time. So this time we'll use this orange color. So we're going to do it one more time. So this also has a length of r. If we connect this to the center, now we have this angle. This angle is 3 radians, is 1 radian. So now from here to here, we have 3 radians. And it turns out that from here to here, and I'll put this in black so it's very clear, this angle over here, this is approximately 0.14 radians. So if we take that string and we lay it out along the arc of the circle, we can lay it out 3.14 times and we'll get to halfway through the circle. Okay? Now what does this mean? We know that from here to here is 180 degrees. We labeled that on our axis over here, right? If we start here and we go halfway around the circle, we're at 180 degrees. So what does this tell us? This tells us that 180 degrees is equal to exactly pi radians. This is equal to pi radians. Okay, and it turns out too that, so this is exact. It's exactly pi. That's why I say that this is approximately 0.14, because it's like 0.14159 and so forth. Okay. So 180 degrees is equal to pi radians. Now, the reason why we use radians, there are a few reasons. One big reason is that a lot of formulas are made much easier because we're using radians. So for example, if I wanted to find the length of this arc, if I'm in degrees, it's a much more complicated formula than just saying, oh, it's the length of r, okay? And what I could do is I could just, so we're not going over the formulas for arc length. We're not going over the formulas for the area that's within this section of the circle. Okay, but if we did, you would see that the formulas are much simpler when we deal with radians. Another reason why we deal with radians is that it's a much smaller unit, okay? In the sense that in a circle, in half a circle, instead of there being 180 of them, there are only about 3.14. In a whole circle, we have 360 degrees. But for radians, we only have approximately 6.28 radians. So we're dealing with much smaller numbers, which makes our life much easier, particularly when we get to graphs later on. Okay, so this becomes much simpler. Okay. Okay, so let's start converting then. If we know that 180 degrees is equal to pi radians, so just a note before we do conversions, it's not necessary to write the unit. In other words, if there is no unit, the angle is in radians. That's what we're saying here. Okay, if there is no unit. So just like if there is no index in a radical, it's a square root. If there is no exponent of x, it's x to the first power. This is the same type of thing. If there is no unit, it's radians. That's because radians is used so frequently, and mathematicians can be very lazy. We don't want to put in the unit. And we can do that because there are not all that many different types of measurement. Think about the English standard system and the metric system, right? Metric system, we have kilograms, kilometers, millimeters, centimeters. We have loads. We have all of these different units. In the English standard system, we have pounds, ounces, inches, feet, yards, miles. We have lots and lots and lots of different units. So we wouldn't just say, okay, well, for this one out of the many different units, we're not going to write anything. Whereas here, it's essentially we have degrees, minutes, seconds, and then we have radians. So we can say, well, if there's nothing written, then we would say it's in radians, okay? So if there's no unit, then it's in radians. So we would say 180 degrees is just equal to pi. We wouldn't put the radians, okay? So if 180 degrees is equal to pi, now we can actually go through and we can figure out, for example, what 90 degrees is. So if you think about it, it's kind of obvious, right? 180 degrees is pi, 90 degrees is half of 180. So what's half of pi? We would just write pi over 2. And you always leave it in terms of pi. The reason why you leave it in terms of pi is it's so much more accurate, right? Pi is an irrational number. Anything that you write would be an approximation, so you would leave it in terms of pi. 45 degrees. Well, 45 is half of 90, so if we take pi over 2 and we divide that by 2, then it would be pi over 4. Another way to look at it is 45 degrees is 1/4 of 180 degrees. So this is equal to pi over 4. 360 degrees. Well, 360 degrees is double 180. So 360 is double pi. So 360 is 2 pi. We could even go down here to this 270 degrees. Well, 270 degrees, it turns out, is 1.5 pi, right? Here's 1 pi, and then we're going another half pi. So 1.5 in fractions is 3 halves. So it's 3 pi over 2. So before we go any further, let's go back to our unit circle and put in how many radians each of these are. Okay, so this is 0 degrees. This is 0 degrees or 360 degrees, but it's also I didn't need to do that. It's also 0 or 360 degrees is 2 pi. And sorry for all of this formatting. I'm going to include this in the board notes. So I want to just make sure that it's clear. Okay. So it's 0 or 2 pi radians. Now when we get to 90 degrees is the same thing as pi over 2 radians. So 90 degrees is equal to pi over 2. Now 180 degrees is equal to 3 pi over, is equal to, I'm sorry, I didn't even have to do that. 180 degrees is just equal to pi. Okay, so at 0 degrees, we're at 0 radians. At 90 degrees, we're at pi over 2 radians. At 180 degrees, we said that we're at pi radians. At 270 degrees, we said that we're at 3 pi over 2 radians. And then when we go back to 360 degrees, we're at 2 pi radians. Okay, and what else does that mean? That means that the sine of 0 radians is 0. The cosine of 0 radians is 1. The sine of 2 pi radians is 0. The cosine of 2 pi radians is 1. The sine of pi over 2 radians is 1. The cosine of pi over 2 radians is 0, and so forth. So the sine and the cosine of 180 degrees is the same as the sine and the cosine of pi. Okay? And same thing here. Sine and cosine of 270 degrees is the same as the sine and the cosine of 3 pi over 2. Okay? Okay, but it's not always this simple, right? Because what if we wanted, for example, 35 degrees in radians? Now this is a little bit harder because 35 degrees, like 180 degrees, is pi. So we found that 90 degrees was pi over 2 because 90 degrees is half of 180. Okay, so half of pi is pi over 2. 45 degrees is a quarter of 180, so it's pi over 4. So the thing is that 35 degrees, we can't do that. Okay, 35 degrees is not a factor of 180. So how do we convert from degrees to radians? Well, it's actually a relatively simple process because we can just do a part to a whole proportion. Okay, so we could say part to whole is equal to part to whole. And one side of this is going to be your degrees. And one side of it is going to be your radians. So what we're asking is, what part of 35 degrees what part is of 180 degrees is 35? And whatever that part is, that's equal to x over pi. So our whole, now you could use 360 degrees and 2 pi so that you're thinking of it as whole circle is equal to whole circle, or you could use 180 degrees over and pi and 2 pi. So either way, your wholes is the whole piece. So you could think of it as half circles or whole circles. It doesn't matter, okay? So you have 35 over 180 is equal to x over pi. Well, what do we need to find? We need to find x. So our x This is the angle in radians. That's what we're trying to find. So we can cross multiply. Sorry, 35 pi is equal to 180x. Okay, if we are general about it, we could say theta over 180 is equal to x over pi. So notice that the 180 and the pi will never change. Okay, so when we cross multiply, we get 180x is equal to theta times pi, and then x is equal to theta times pi over 180. So that will always be true. So we can generalize it and say, well, to convert an angle from degrees to radians, you just take the angle that you're given and you multiply by pi over 180. But this is why, because you're constructing a ratio where you have part to whole is equal to part to whole. You cross multiply and you're solving for x. So we divide both sides by 180. Okay, and just like always, you always want to reduce. Okay, so our x is equal to 35 pi over 180. Leave it in terms of pi, but reduce. So both of these are divisible by 5. So it's 7 pi over 36. And this would be the angle in radians. Okay, so you're leaving in terms of pi, but you're reducing. Let's take another one. So we do the same thing. Part to whole, it's okay that our part is bigger than our whole, is equal to x over pi. So 200 pi is equal to 180x, or x equals 200 pi over 180. And you want to reduce. So both of these are divisible by 20. So you get 10 pi over 9. Okay, so you reduce, but you leave in terms of pi. Don't convert this to a decimal. Okay, and don't convert your improper fraction into a proper fraction. Leave it as 10 pi over 9. Okay, let's do one more. Let's say that we have 50 degrees. So you do the same thing. You have your 50 degrees over your 180. Part to whole is equal to part to whole. Okay, you cross multiply, you get 50 pi is equal to 180x, and then x equals 50 pi over 180. These are both divisible by 10, so you get 5 pi over 18, okay, in its reduced form. Okay, so this isn't that bad. Okay, you're setting up, you're always multiplying by pi over 180. Notice in each of these, we multiply by pi over 180. That's what's happening in all of them. We're multiplying by pi over 180. Okay, and the reason why this is an improper fraction is because 200 degrees is greater than 180 degrees. So this here should be greater than just pi. We multiplied 35 by pi over 180. Okay, so let's convert from radians to degrees. Okay, so typically our angles and radians are in terms of pi, meaning that the angle that you're given has a pi in it. But let's say it doesn't, okay? So we have two different possibilities. If the angle in radians is not given in terms of pi, right? We could be told that the angle is 1.57 radians. That's fine. There's nothing wrong with that. Okay, we typically leave it in terms of pi because when we plug it into our formulas, it makes our life much easier, but we don't have to. Okay, so here, let's suppose that we have 1.57. Well, if we do that, you're still going to use the part to whole over part to whole. You're still going to do degrees and radians. Here's your degrees. Here's your radians. So what does that give us? Same thing that we had before. It's our angle in degrees over the 180 is equal to our angle in radians over pi. That hasn't changed. So we cross multiply. We still get pi theta is equal to 180x. The difference is that we're not trying to find x anymore. We're trying to find theta. Okay, so now instead of dividing both sides by 180, because we know x, we're going to divide both sides by pi. Okay, that's going to cross this out, leave theta by itself. So notice what is happening here. Instead of multiplying the angle by pi over 180, we're multiplying the angle by 180 over pi. I'll write it as 180x because x 180 is such messy looking. Okay, so you're still setting up your part to whole equals part to whole. It's just that you're solving for theta now instead of solving for x. So instead of multiplying by pi over 180, we're multiplying by 180 over pi. So that means that if we're converting 1.57 from radians to degrees, we have theta over 180 is equal to 1.57 over pi. We cross multiply 180 times 1.57 is equal to theta times pi, or theta is equal to 180 times 1.57 over pi. And this is an angle in degrees. You would not leave it in terms of pi because it's an angle in terms of degrees, because it's an angle in degrees. So you would actually multiply 180 times 1.57 and then divide by pi, and pi is on your calculators. Okay, and this would give you 89.95 degrees. Okay, so it's an angle in degrees, so you would not leave it in terms of pi. Convert it to a decimal. Let's do one more. Okay, let's convert .81 radians to degrees. Okay, so once again, we're going to set up our part over whole. So the degrees, the angle in degrees is unknown. So notice we're using theta because that's like a variable for angles. So theta over 180 is equal to 2.81 over pi. We can cross multiply here. So we get 180 times 2.81 is equal to theta times pi. And then we're dividing both sides by pi. So remember, this is the same thing as taking our 2.81 and multiplying by 180 over pi. It's just doing the opposite, right? The reciprocal. And once again, you would not leave it in terms of pi. You would actually put this into your calculator. Do 180 times 2.81 divided by pi. Again, pi is a button on your calculator. And you get 161.00 degrees. Okay, make it a habit to round to the nearest hundredth. I like the nearest hundredth. Okay. Now there's the other way to do this too. This is if the angle isn't in terms of pi. If the angle is in terms of pi, then it's really simple. We could just replace pi with 180 because pi equals 180. Okay, so for example, let's say that we want to convert 5 pi over 6 to degrees. Well, we have a pi in here. So what we're going to do is we're going to take 5 and we're going to replace the pi with 180 degrees. And if we do 5 times 180 over 6, we get 150 degrees. Okay, so notice I put 180 degrees in there because I want it to be clear that when we replace pi with 180, we're changing the units. Let's do one more. Let's convert 2 pi over 7 radians to degrees. So once again, it's nice and simple. We just take 2, and instead of multiplying by pi, we can multiply by 180 degrees. And we get 51.43 degrees. Okay, so nice, simple way to convert. And a lot of times you're going to be converting from degrees to radians. Sometimes you'll be converting from radians to degrees. There are going to be times when you're more comfortable working in degrees, so you're going to find the angle in degrees and then convert to radians, or vice versa. But you should be pretty comfortable with both, okay? So very quick summary of what we did, because there was a lot in there, okay? We first looked at the unit circle. We defined the unit circle as a circle with radius 1 and center at 0, 0. And we said, okay, well, first, what's the equation of the unit circle? So to find an equation, we look at a relationship between x and y. That's what every equation is. It's some relationship between the x and the y values that will give us all the points on the graph. So we took any point on the circle and we labeled it x, y, and then we saw that we could create a right triangle using that, okay? So when we create the right triangle, the horizontal distance is x, the vertical distance is y, because to get to the point x, y, we go over x and up y, and the diagonal, or the hypotenuse, is 1. So using the Pythagorean theorem, the relationship that we get between x and y is that x squared plus y squared is equal to 1. Okay. Now we said that we could do the equation for any circle with center 0, 0. Okay. The equation would just be x squared plus y squared is equal to r squared. So instead of having a radius of 1, we have a radius of r. And then if the center is at c comma d, then it would be x minus c squared plus y minus d squared is equal to r squared. Okay, that would be the equation for any circle with a center at c comma d, and that's because this is just a translation, okay? Okay, so then what did we do? We said, okay, well, this means that we call this angle theta. When we travel around a circle, we travel counterclockwise around the circle. And this is our starting point. And we're going to talk about this more in the next lecture. So here we have quadrant 1, we have quadrant 2, quadrant 3, quadrant 4, okay, traveling this way around the circle. So this is where we start. So this angle here would be called theta. And we said, okay, well, the sine of theta is equal to y over 1 in the unit circle. So our y values here are the sines of the angles. And the cosine of theta is equal to x over 1. So the x values here are the cosines of the angles. We were able to label the angles. So if we start here, that's 0 degrees, we also say that it's 360 degrees because when we go all the way around the circle, we're right back here. This is 90 degrees, this is 180 degrees, this is 270 degrees, and then again back to 360. Now we also labeled these angles in terms of radians. So in radians, this is 0, this is pi. Then we found that pi over 2 would be up here because this is exactly halfway to pi. This is 1.5 pi, so it would be 3 pi over 2. And then when we come all the way back around, we've went 2 halves of the circle, so we're at 2 pi, okay? Then we said, okay, well, let's do more specific conversions between degrees and radians. So to convert from degrees to radians, we could do a part to whole is equal to a part to whole, where one side is the degrees part to whole, and the other side is the radians part to whole. And we set it up as, okay, well, here's our angle in degrees. Our whole is 180 degrees. Again, you could use 360, but if you use 360, this should be 2 pi. And then our parts are the angles in degrees over here and the angle in radians over here, okay? Then we could just cross multiply. So depending upon what we're given, the other numerator is what's unknown, and that's going to be, we're always going to get pi times theta equals 180 times x. And if it's degrees to radians, we're going to be dividing by 180. If it's radians to degrees, we're going to be dividing by pi, okay? Over here, when you convert from degrees to radians, you leave your answer in terms of pi, but you reduce as much as possible. Now, if you're converting from radians to degrees, but your answer is given to you in terms of pi, you don't have to do that ratio. You can, but you don't have to. You can take the pi and just replace it with 180 degrees, and that'll give you your angle in degrees. Okay? And that is it for this lecture. It may take me a minute to pause, so stop listening now.